Welcome to our EMT lecture series number 4. At the end of this lecture, students are expected to understand and able to apply Coulomb's law in calculating electric field intensity due to line and surface charge distributions. In this course, we will look only into applying Coulomb's law for the case of charge distribution along a thin line or on a surface, given that its calculation for the case of a volumetric charge distribution is complex. We will use other approaches to handle such cases. Previously, we have described that Coulomb's law defined the force that exists between two charges or two groups of charges. Based on Coulomb's constant, magnitude of charges, as well as separation distance. For a condition where the surrounding is a vacuum, the value of free space permittivity or epsilon naught is being used to define Coulomb's constant. The force experienced by a charge or a group of charges due to other charge or charges within a surrounding space region is defined as electric field strength or electric field intensity, symbolized by E. Let's try to analyze line charge distribution. Supposedly there's a line with length L having charges throughout the line described by the line charge distribution ρL. We would like to observe electric field due to the charges on the line to an observed point P. To do so, we would apply Coulomb's law. To apply Coulomb's law, we first need to identify small charges from the line. Supposedly, we call these charges dq that is residing within differential length dl. Then, we will determine the differential electric field from dq to the observed point P. Given that ρL is applicable throughout the line, we would then determine total electric field by integrating dE. To continue solving the problem, we would define boundary of the line as A and B. Also, to apply Coulomb's law, we need to specify the coordinate system. It is quite normal to apply cylindrical coordinate system for the case of line charge. Supposedly, point P has a coordinate of x, y, and z, and dq has a coordinate of 0, 0, z prime. Thus, the length between dq and this point is given as z prime minus z. The upper boundary B to this point here, length, is equivalent to B minus Z, whereas the point here to the lower boundary A is given as Z minus A. The vector from the source of electric field to point P that is being observed is defined by vector R. Vector R can be shown to have a value as x in the x direction plus y in the y direction minus z prime minus z in the z direction. In cylindrical coordinate, R has a value of z prime minus z in the negative z direction plus R in the R unit vectors or R direction. The magnitude of the vector is as shown. Now, dq is defined as ρL dl, and we would use this definition to define the dE. In order to determine the total electric field from the whole line to the observed point P, we would integrate dE. Applying the cylindrical definition of vectors and magnitude, we would have E as in the shown equation. In order to solve the problem, we need to multiply the mathematical terms here with the mathematical terms here, in which we would get now the integration is with respect to dz prime. As we simplify the integration by factoring out rho L divided by 4 pi epsilon naught, we would get this relation for E field. In order to solve this, it is easier if we are to apply the following integral identities. By applying the following integral identities to the given problem, we will solve the integration as shown on the slide. Now, if we are to insert the value b and a, the boundary of the line, to our problem, we will get the following lengthy solution to E field. The equation to determine electric field from the line to the observed point P is rather complex based on the provided steps shown. We can simplify the relation. Let's look at this illustration here. This is angle alpha 2 and this is angle alpha 1. Sine of alpha 2 is given as b minus z over the length of this line here, that is equivalent to the square root of r square plus b minus z square. Whereas sine for alpha 1 is given as z minus a divided by the length here, which has a value of square root of r square plus bracket z minus a square. We can also define cos alpha 2 and cos alpha 1. The descriptions shown for the sine and cosine of alpha 1 and alpha 2 can be applied to this relation, such that we would get electric field to be defined by this more simple mathematical relation. What would happen if we are to have A and B having infinite value, such that this line here is an infinite length line? Alpha 2 and alpha 1 would be of an angle 90 degree. And electric field thus for an infinite length line charge would be given as the following relation. Let's solve this as homework. Now, as in the case for line charge distribution, we can also apply Coulomb's law in order for us to determine what is the electric field at a particular point on a surface. Say, for example, we have a surface plane and we have a point P where we are in need to determine electric field at this point. So basically, to apply Coulomb's law, what we'll do is that to determine or identify one sample of surface, ds, and within the surface, we are going to analyze dq, charge element dq within that surface, having or defined by rho s ds. And this charge element will be the source of electric field at point P. Next steps, we are going to define differential element electric field as be equivalent to rho s ds divided by 4 pi epsilon naught r square in the r unit vectors. And the third step is to integrate this dE in order for us to determine the total electric field due to the whole surface area. We can use the previous technique in order for us to determine electric field due to any finite surface area. For a case of an infinite surface area, we have to do additional so-called analysis, and let's consider the case for a circular surface charge having a surface charge density of rho s, and the circular surface having a radius of a, centered at origin and lying on the z equivalent to 0 plane. We are going to use circular coordinate system in order to solve this mathematical derivation. Alright, based on previous assumption, let's try to look at this case. We are going to determine electric field at point P having coordinate 0, 0, z, and let's consider a circular area with radius a that is infinite. To determine electric field at point P, again, we need to take up one sample of area, or ds, differential surface from this total circular area. And let's suppose ds would have some sample of charges dq, and the electric field due to dq to this point P is along the vector r. dq will be equivalent to rho s ds, and ds due to cylindrical coordinate system will be defined as r dr d phi. Based on Coulomb's law, we will have this relation of electric field as well as applying of determining it based on dq divided by 4 pi epsilon naught r square. For a cylindrical coordinate system shown in the illustration, r vector would be determined as equivalent to r in the negative r unit vector, r in the negative r unit vector, since it is opposite or going inwards toward the direction of the origin, plus z in the z unit vector directions, plus z in the z directions. And the magnitude would be given as r equivalent to square root of r square plus z square. Defining this and applying it to the relation of dE equivalent to rho s ds divided by 4 pi epsilon naught r square, we would have this relation. If this is just a sample of differential electric field due to ds, and we are going to define electric field for the whole case of total area, we would usually integrate dE. But let's also consider that for a particular differential surface here, due to this circular surface area, there would definitely be an equivalent 180-degree differential surface that will also have that will also become electric field source that will inflict point P here. What is the electric field or differential electric field due to ds over here? It would be similar to the calculated equations, with exception that if we look at the illustration, the r part here, the vector is no longer in the negative r, but rather it would be in the r directions. So eventually, due to symmetrical conditions, what we'll have is that the negative r in the negative r unit vector would eventually be cancelled out. Having said that, if we are to solve the integration of dE, we would end up with this mathematical relation. If we are to apply these integration mathematical identities to these mathematical relations, we would arrive to this relation of electric field. after solving the integration. Continuing to solve the mathematical derivations by putting the infinite and zero limits value to our solutions, we would end up with these relations in which we can eventually summarize for an infinite surface area, the electric field due to it would be equivalent to rho s divided by 2 epsilon naught and n, which is the unit vector for this electric field. Let's try to solve this as a homework. Given that a circular disc is having a radius of 5 meter and there's a total charge distribution of 500 pi microcoulomb, total charge distribution on the surface. And the surface is located at z is equivalent to 0. If a point charge of 50 microcoulomb is placed at coordinate 0, 0, 5, try to find the force acting on that particular point charge here. Students, let's do this as a homework. Alright, now we have arrived for the case of volume charge distribution. For volume charge distributions, we are not going to apply Coulomb's law in solving these problems, given that the steps involved are quite complex. Therefore, we are going to only use Coulomb's law for line charge distribution and surface charge distribution. We will solve for the case of volume charge distribution using other technique. To summarize what have been taught in lecture 3 as well as in lecture 4, we are expecting students to be able to understand the concept of electric charges as the source of electric field and the concept of electric force, electric field, as well as the Coulomb's law. And finally, to apply Coulomb's law in order to determine electric field induced by specific charge distribution. In our next lecture, we are going to discuss on electric flux density, and Gauss law.